You know, I was holding a peacock feather the other day, just turning it over in the sunlight, and I had this realization: the incredible blue and green. It's not pigment, not like paint. It's pure physics. It's nanoengineering. And today we're going to unpack that exact connection, the hidden physics that links a peacock's feather to the fastest, most efficient lasers we can build.
It's a perfect example, isn't it? Nature as the original engineer. So our mission for this deep dive is to really get into structural coloration
Hmm.
and then show how scientists are basically mimicking these tiny nanostructures to change data communication.
Yeah.
We're talking about photonic crystals and this amazing thing called slow light.
What gets me is that structural color is all about geometry controlling light. So instead of a chemical absorbing colors, you have these periodic microstructures, right? Like on opals or butterfly wings, and they diffract light into different colors depending on the angle you're looking from.
That angle dependency is absolutely key, and it's
Yeah.
already made this huge leap from the lab into the real world. Think about banknote security.
Oh, really?
Yeah. A lot of international currencies, the US dollar, the euro, they use this optically variable, structurally colored ink.
Wow, that's such a great example. So you start with a feather and end up protecting global finance. And I guess because a copier only sees light from one angle.
Exactly. It just can't reproduce that color shift. It's a brilliant security feature. And it's amazing to think this idea goes all the way back to Lord Rayleigh in, 1887. He was studying these 1D structures, and that work eventually led to the whole concept of photonic crystals in the late 80s.
Okay, so let's connect that to today. The big goal is to manufacture artificial versions of these structures,
Oh.
photonic crystals or PHCs.
Right. And we build them to control the flow of light, pretty much right on an integrated circuit chip.
So how does that work? Are they like tiny wires for light?
More like a really sophisticated sieve.
Yeah.
Or a traffic control system. We designed them to create something called a photonic band gap. You can think of it as a forbidden range of light frequencies.
Okay, so a band gap, almost like a no-go zone for certain colors of light.
That's a great way to put it. It means we can force light down specific paths, or even slow it way down.
And that must be how we get density. The dream is to use these two-dimensional PHC slabs chips with these incredible patterns etched into them to make ultra-compact things like lasers and switches that trap light in a space that's barely bigger than its own wavelength. I mean, building things on that scale must be almost impossibly difficult.
The precision required is, well, it's extreme. To get them to work, you have to integrate active materials, things that actually emit light, like quantum wells, directly into these tiny structures. The challenge is making sure every interface is atomically clean. You're essentially weaving light-emitting layers into the fabric of the crystal.
And this is where it all pays off, right? The performance we're seeing. I read about weak lasers achieving these incredibly low energy costs, something like 4.4 femtojoules per bit. That's just a revolutionary leap in efficiency.
It is. And the secret to that performance is an effect called slow light. Inside these PHC waveguides, the light is sort of bouncing around the structure, which slows down its effective speed. We call it group velocity.
Speed bumps for light, basically.
Exactly. And when you slow the light down, you dramatically increase the time it has to interact with those active materials inside the chip.
And that interaction time is everything.
It is. More time means more energy extraction, a bigger signal. Experiments have actually measured this, amplifying the emission with a group index that's Mundollars of up to 18. That means light is traveling 18 times slower than it normally would, which is huge for getting more gain out of a tiny device. This whole level of precise control and automation is what lets us build these systems.
You know, speaking of precise control and automation, this deep dive is sponsored by Embersilk. Just as nanophotonics needs that perfect engineering to integrate everything, your business probably needs the right integration and automation to thrive. So if you need help with AI training, automation, software development, or even just uncovering where AI agents could make the biggest impact for you, check out embersilk.com for your AI needs.
So what does all this mean for you, for the future? It means the next generation of telecom and computing. It's not about brute force. It's about borrowing the elegance and the intricate geometry from nature's own art. We're taking the secrets from a peacock feather to build faster, smaller, and vastly more energy-efficient optics for the entire world.
That's really the most hopeful part of this, I think, realizing that the most powerful solutions are often the smallest and, well, the most elegant. If you enjoyed this deep dive into the fascinating world where structural color meets nanophotonics, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.